Hello, my dear students. In today's video, I'll be talking about part 1 of a long series of lectures on microelectronics. And in this first part of the lecture, I'll be talking about resistors, specifically the carbon type resistors. Resistors are the most common components in electronic equipment. It is manufactured with a specific value of ohms for its resistance R. And the construction used most often is the carbon composition type, as shown in this photo. These are what we call fixed carbon type resistors, and uh, they are labeled in terms of their resistance by the color bands or stripes that you see in the outside coating. So if you're going to look at the inside of a carbon composition resistor, you would see there of course, the protective coating on which the color bands are printed. There is a thin film inside, and the carbon material are in helical cuts. This is to reach the desired resistance value, and a ceramic material is used as a carrier. Of course, you have here the end caps made of leads. So these are the type of resistors that we're going to be talking about. There are other types of resistors used in uh, electronics. Some are what we call variable resistors. These are just some examples of different types of variable resistors. We say that resistors are intended or used in a circuit to either reduce the current to a specific value or also to provide the desired voltage in a circuit, just like what is shown here in this circuit board. The two main characteristics of a resistor are its resistance, labeled capital R, which is expressed in ohms, and its power rating, labeled capital W, expressed in watts. Resistors are available in a very wide range of R values, from a fraction of of an ohm to many kilo ohms. So this abbreviation is read as kilo ohm and megohms. The abbreviation capital M with that ohm symbol is read as megohms, shortcut for mega ohms. That's also true for kiloohms, shortcut for kilo ohms. The power rating for resistors can be as high as several hundred watts, or could also be as low as 1/10 of a watt. And most common in electronic equipment are carbon resistors with power rating of 1 watt or less. Resistors with higher R values usually have lower wattage ratings because they have less current. As an example, a common value of 1 megohm at just 1/4 watts for a resistor only is 1/2 of an inch long. The lower the power rating, the smaller the actual physical size of the resistor. However, the resistance value is actually not related to physical size. All right. Um, the meaning of wattage rating is just actually the ability of the resistor to what you call to tolerate, okay, the possible increase in the power, okay, if the power in the circuit reaches a value that is much higher than the power rating, that means the resistor will be damaged. So, because carbon resistors are small physically, they are color-coded to mark their R value in ohms. And the basis of this system is the use of colors for numerical values, as listed in the table below. Alright, so as shown here, uh, there are carbon type resistors which have three band or three stripes, alright, of colors. Others are also in what we call four band, meaning with four stripes of colors, alright. But others could have five up to six color bands, alright. So, the different colors, starting with black, the dark colored or the dark colors such as black and brown. Black represents the digit 0, all right. For brown, it is the digit 1. Red is 2. Orange is 3. Yellow is 4. Green is 5. Blue, 6. Violet is 7. Gray is 8. All right. And also, there's uh, the lightest color, which is white, which represents the digit 9, right? And then the most commonly used colors or color bands to represent what we call the tolerance level, all right, are the color silver as well as gold. Okay, so when we say tolerance or degree of tolerance, that means uh, we are saying that a particular color-coded resistor can have a value. Say, for example, the last color band is silver, okay, that represents the tolerance level. We say that whatever is the actual ohmic value, okay, in reality, it ranges from that value with a degree of tolerance such as plus minus 10% when it is color silver. But when it is color gold, then the tolerance is plus minus 5%. All right, you'll be talking more about this degree of tolerance in our examples. All right. Uh, in resistors with what we call 5 color bands, okay, uh, we say that a 5 color band resistor is more what we call more accurate than the 4 color band resistors. Okay. Normally, okay, normally the last color band, for example, in a 4 band resistor, the fourth band would represent what we call uh, the degree of tolerance, while the third band represents the multiplier. All right. So, for example, the third band has the color black. It means that the first 2 digits that represents the actual ohmic value, okay, will be multiplied by a factor times 10 to the 0 power, meaning 1. When the third band has a color brown, that means the multiplier is 10, 10 to the first. When it is red, the multiplier is 10 to the second power, or 100, and so on. Okay? And there is a pip color or pip band. This is true for 6 band resistors. And that 6 band or stripe represents what they call the temperature coefficient, all right, expressed in parts per million per Kelvin. We will have a detailed explanation about the 6 band in one of our examples to follow. All right, for our first example, given the different bands or color bands in this illustration, supposing the first band, which is actually the first digit, is colored red, the second band is colored green, the third band is colored red, and the fourth band, or band D, is colored gold. So our task is to find the ohmic value for this resistor as well as its degree of tolerance. All right. So if you notice the way the color bands are printed on the coating, the outside coating of a regular carbon type resistor, you will notice that uh, the first three colors, or the first three color bands, are closer to each other, and they're closer to one end. All right, they are closer to one end of the resistor, the left end usually. Okay, and then the fourth band is somewhat distant, a little distance away from the first three. All right, so you will know which color band is used for determining the tolerance. All right, because it is somewhat printed a little distance away from the other first three. All right, and it's usually either gold or silver. But there are resistors with no degree of tolerance. All right, there is no fourth band. If gold represents 5% plus minus 5%, all right, tolerance, and silver represents plus minus 10%, when there is no fourth band, it simply means that that particular resistor is understood to have a tolerance of plus minus 20%. Okay, again, if there is no fourth band, it's understood that the tolerance is plus minus 20%. So in this first example, we are going to determine the actual ohmic value and the degree of tolerance. We'll see the solution in our next slide. So our solution for question number 1, we are going to use this uh, guide. What shown in the table are the corresponding digits for each color, starting from black, brown, red, orange, yellow, and then green, blue, violet, gray, and white. You will notice that the colors starts with the darkest colors, such as black, brown, and then if you notice from red down to violet, that's in fact ROYGBV. All right. Of course, The lightest colors, such as gray and white, corresponds to the last two digits, 8 and 9. So for a given uh, color bands, where the first digit, the first color band is red, so it's equivalent to digit 2. For green, it's equivalent to 5. Red, again, is 2. And the degree of tolerance has gold as its color. That means our level of tolerance is plus minus 5%. And so we now have the ohmic value of this resistor. First two significant digits are 2 and 5. And the multiplier is times 10 to the second power, or 100. And then the degree of tolerance plus minus 5%. Simplifying, all right, we get the 5% of 2,500 ohms, which is uh, to be added to 2,500, and for the lower limit to be deducted from 2,500. Therefore, our final answer for the range of this resistor is uh, a resistance value that ranges from 2,375 ohms to 2,625 ohms. All right, so that means if you're going to measure the actual ohmic value using a multi-tester or an ohmmeter, and for as long as the measured value of the resistance falls within this range, we say that that particular resistor is safe to use. All right, but supposing the measured value is not within the range, instead the measured value is lower than 2,375 ohms, or possibly greater than 2,625 ohms, it only goes to show that that resistor has a factory defect, and you should not uh, use that resistor anymore. Better replace it with a value of resistor, all right, that has the correct value falling within the given range. To help you out in memorizing the equivalent number for each color band, starting from black down to color white, I am suggesting the following mnemonic device. So we say, starting from black, bad, boy, rape, hour, young, girl, but Violetta gave in willingly. Question number 2. What is the ohmic value of the resistor shown in the figure? Alright, so the figure shows uh, a special kind of resistor having only three color bands. The first band is colored brown, the second band is black, and the third band is colored gold. So this kind of resistor, okay, is an example of a resistor whose actual resistance is below 10 ohms. Right. So for these values, the third stripe could either be gold or silver, indicating a fractional decimal multiplier. So just like in our drawing, the third stripe is gold. So what you'll do is multiply the first two digits by 0.1. If this third band is silver, okay, that would mean a multiplier of 0.01. So, for this particular type of resistor, our first color band or stripe is brown, so the first significant digit is 1, while the second band is black, corresponding to the digit 0, and the third band is gold. So what we are going to do is multiply the first two digits by 0.1, all right, and that would mean the actual value of the resistance for this resistor is 10 times 0.1 ohms, or exactly 1.0 ohm. There is no specified degree of tolerance. Question number 3. What is the ohmic value of the resistor shown in the figure? Alright, so in our figure, the first color band is green, the second color band is violet, while the third color band is red. Apparently, there is no fourth band to represent the degree of tolerance. But in this case, we have mentioned earlier that if there are only three bands, alright, it's understood that the degree of tolerance is plus minus 20%. Okay, without a fourth stripe or fourth band, okay, it's understood that the degree of tolerance to be taken is plus minus 20%. So, since the first band is green, its equivalent is 5. Violet is 7, and the third band is red, therefore 2. Hence, okay, the value or the ohmic value is 57 multiplied by 10 to the second power, or 100, and then the degree of tolerance is understood to be plus minus 20%. And therefore, if we calculate for the 20% or 0.20 of the ohmic value, which is 5,700 ohms, we have this range, all right? 20% of 5,700 is in fact 1,140 ohms. So if you're going to get the upper limit or the upper value of the resistor, it is 6,840 ohms, and the lower value limit is 4,560 ohms. So then again, upon measuring using a reliable multi-tester, just make sure that the actual measurement range or falls within this range, okay, for you to be able to make use of this resistor, and you are assured that it is safe and it has no factory defect. For our question number 4, what is the ohmic value of the 5-band resistor shown in the figure? Alright, so in the figure we have the first color band, which is brown, followed by black, and then another black. The fourth band is brown, while the fifth band is colored red. Alright, so determining the equivalent value of each color. For brown is 1, for black it is 0, the third color band is again black, so 0, and the multiplier, which is the fourth band, is times 10. Alright, while the degree of tolerance is red, so it means that red as a degree of tolerance represents plus minus 2%. So calculating for our ohmic value or range value of the resistor, we have for the three significant digits 100 or 100, ohms, that will be multiplied by 10 ohms. Okay, and the degree of tolerance is plus minus 2%. Okay, further calculation of the value of 2% of 1000 ohms, right? We will get uh, the 20%, or the value of 0.02 times 1000, of course, is 20 ohms. So to get the range value, we have just to add 1000 ohm. Okay, we just add 20 ohms to 1000 ohms and get 1020 ohms. And the lower value, the lower limit, is just deduct 20 ohms from 1000 ohms, and that is 980 ohms. So the safe value range for this particular resistor, therefore, is from 980 ohms to 1020 ohms. Before we discuss the last question, we'll first talk about resistors having a 6-color band, right? So the 6th color band represents the so-called TCR, also known as temperature coefficient of resistance. So this TCR means, or also means, that the rate at which the resistor changes with change in temperature. Example, if the 6th band is colored brown, and according to our table, when brown is the 6th color, okay, the TCR value is 100 parts per million per Kelvin or Celsius degree. All right. So this means that for every 10 Celsius degree change in temperature, or 10 Kelvin change in temperature, okay, the resistance value will change by 0.1%. And we have our example, the last question. Question number 5, what is the ohmic value of the 6-band resistor shown in the figure? Right? So, determining the corresponding value of the different colors, the first band is red, so that's 2. Second band is violet, so that's 7. The third band, which is 4. All right? The fourth band indicates the multiplier black, so that means the first 3 digits will be multiplied by 10 to the 0 power, which is equivalent to 1. For the fifth color band, which is red, and red as a degree of tolerance, corresponds to plus minus 2%. And the last color band, which is brown, its coefficient of temperature is equivalent to 100 parts per million per Kelvin. All right, so determining the range value, we have the first 3 digits, 274, to be multiplied by 10 to the 0 power, or 1, and then plus minus 2% of 274%. So what we get is the 2% of 274 is equivalent to 6 ohms rounded to the nearest whole number. So that means our final range for the ohmic value is from 268 ohms to as high as 280 ohms, okay, with the coefficient of temperature value 100 parts per million per Kelvin. So we are done with our calculation, and uh, for the video tutorial of the first part, hope to see you in the succeeding parts that will come very soon. Thank you very much for your indulgence.